Imagine it now. A city on Mars. Glass domes catching the pale sunlight, reflecting it across fields of green where crops grow in controlled environments. Children running through pressurized corridors, laughing as they look up at the rusty sky through transparent ceilings. Solar panels stretching across rust-coloured plains like metallic forests. Rovers moving between settlements, carrying supplies, carrying hope. The flags of Earth nations and new Martian colonies flutter in artificial breezes. Humanity, triumphant, planted on a second world. No longer confined to a single fragile sphere, but scattered across the solar system, resilient, infinite, eternal. This is the dream. The vision sold to us through countless documentaries, billionaire promises, and science fiction narratives that have seeped so deeply into our collective imagination that we've begun to mistake aspiration for inevitability. We see the artist renderings, we hear the launch dates, 2035, 2040, 2050 at the latest. Mars colonies are not presented as questions anymore, but as destinations, as certainties waiting just beyond the next decade, the next technological breakthrough, the next budget approval. SpaceX builds starships with Mars in mind. NASA refines its Artemis program as a stepping stone to the Red Planet. Movies show us Matt Damon growing potatoes in Martian soil. Elon Musk speaks of making humanity a multiplanetary species with the confidence of someone describing tomorrow's weather. The cultural momentum is undeniable. Mars is not just a planet anymore. It is a symbol, a promise, an escape hatch from the problems we've created here on Earth. Overpopulation, climate change, resource depletion, political division. Mars offers a clean slate, a fresh start, a chance to rebuild civilization without the baggage of history. But what if that dream, beautiful as it is built on foundations that cannot hold? Tonight, we will do something different. We will not feed the dream. We will examine it, carefully, methodically, and without mercy. Because beneath the glossy renderings and inspirational speeches lies a reality so harsh, so unforgiving, that it calls into question whether Mars colonization is not just difficult, but fundamentally, permanently impossible. Not impossible because we lack ambition or courage, but impossible because physics, biology, and engineering impose limits that no amount of money or determination can overcome. This is not a story of pessimism, it is a story of honesty, of looking directly at the challenges that enthusiasts gloss over, that promotional videos conveniently omit, that press releases bury in footnotes. We will journey through the invisible radiation that would silently destroy human cells. We will examine an atmosphere so thin it might as well not exist. We will confront a gravitational field weak enough to unravel the human body over time. We will investigate water supplies that are not liberation, but logistical nightmares, resources that exist in name only, and psychological pressures that no training can fully prepare us for. If you have ever wondered why, despite decades of planning, no human has yet set foot on Mars, this video will provide answers that go far deeper than budget constraints or political will. The obstacles are not merely technical, they are existential. They're written into the fabric of biology and physics itself. This is a deep dive, a detailed examination designed for those who want more than surface-level optimism, for those who find comfort in understanding complexity, who fall asleep not to empty noise but to the rhythm of thorough explanation. If you have been searching for a video that treats you as an intelligent observer capable of handling difficult truths, you have found it. Settle in. Let your mind drift through the science. Let the details wash over you like a gentle tide of knowledge. And if you find value in this journey through reality, please consider liking this video and subscribing so we can continue exploring the universe as it truly is, not as we wish it to be. Before we begin our descent into the Martian nightmare, I would love to know where you are in the world right now. Are you watching this in the early morning hours, unable to sleep? Perhaps it is late evening and you are winding down from the day. Comment below and tell us where you are watching from and what time it is. It reminds us that while Mars may be impossibly distant, we are all here together, scattered across one living world, seeking understanding in the darkness. Now let us turn our gaze toward Mars not with wonder, but with scrutiny. Let us ask the questions that dreamers avoid, and let us discover why the red planet, beautiful and beckoning as it is, may forever remain just beyond humanity's grasp. The dream is seductive, but reality, as always, demands its reckoning. Mars floats in the darkness, a red sphere promising new worlds and fresh beginnings. From Earth, it appears tranquil, even inviting. But there is something absent from Mars, something invisible yet essential, something that makes the very air around our planet shimmer with protection. Mars has no magnetic field, and without it, the planet lies exposed, naked beneath the fury of the cosmos. On Earth, we live within a sanctuary we rarely acknowledge. Our planet's liquid iron core churns and spins, generating a magnetic field that extends thousands of miles into space. This invisible shield deflects charged particles hurled from the sun, cosmic rays travelling from distant supernovas, and radiation that would otherwise strip away our atmosphere and tear through living tissue. We do not see this shield, we do not feel it, but without it, life as we know it could not exist. Mars once had a magnetic field. Billions of years ago, its core was molten, dynamic, alive with the same protective forces that guard Earth today. But Mars is smaller. Its core cooled faster, and when it solidified, the magnetic field collapsed. What remained was a world left defenseless, its atmosphere slowly stripped away by solar wind, its surface exposed to a relentless bombardment of radiation that has continued uninterrupted for eons. To stand on Mars is to stand beneath a sky that offers no protection. Every moment on the Martian surface, invisible particles pierce the ground, the rocks, and anything living. Cosmic rays, born in the violent deaths of stars, travel across the galaxy at nearly the speed of light. Solar radiation, expelled during massive eruptions on the sun's surface, floods the inner solar system in waves of charged particles. On Earth, these forces are deflected harmlessly into space. On Mars, they arrive unimpeded, unfiltered, and lethal. The journey to Mars begins the nightmare long before arrival. A spacecraft travelling from Earth to Mars takes between 6 and 9 months, depending on orbital alignment and propulsion technology. During this voyage, astronauts are exposed to radiation levels more than 200 times higher than what we experience on Earth's surface. The walls of a spacecraft offer some shielding, but not enough. Aluminum, the primary material used in spacecraft construction, can actually make radiation worse. When high-energy particles strike metal, they produce secondary radiation, a cascade of particles that multiply the danger rather than reduce it. Inside the spacecraft there is no escape. Cosmic rays pass through the hull as if it were tissue paper. Instruments measure the accumulating dose, millisieverts per day, adding up over weeks and months. The numbers climb steadily, inexorably. By the time the spacecraft reaches Martian orbit, Each crew member has absorbed radiation equivalent to receiving dozens of full-body CT scans. Their DNA has been damaged thousands of times. Most of these breaks will be repaired by the body's natural mechanisms, but not all. Some mutations will persist, silent and invisible, waiting years or decades to express themselves as cancer. Then, after months of this exposure, the spacecraft descends. The crew lands on Mars, and the radiation does not stop, it intensifies. Mars's thin atmosphere, barely 1% the density of Earth's, provides almost no shielding. Standing on the Martian surface is comparable to standing in low Earth orbit without the benefit of Earth's magnetic field nearby. Every hour, cosmic rays penetrate the regolith beneath your feet, pass through your habitat walls and bombard your body. The annual radiation dose on Mars is estimated at 24,000 millisieverts. On Earth, the average person receives about 3 millisieverts per year. A single chest X-ray delivers 0.1 millisieverts. On Mars, you would receive the equivalent of 240,000 chest X-rays annually simply by existing. The biological effects are not abstract. They are specific, measurable, and devastating. Radiation damage begins at the cellular level, where high-energy particles strike DNA molecules, breaking the delicate double helix that carries our genetic instructions. Most of these breaks are repaired, but errors accumulate. Over time, these errors lead to cancer. Studies of radiation exposure in atomic bomb survivors, nuclear accident victims, and astronauts aboard the International Space Station reveal a clear pattern. The more radiation absorbed, the higher the cancer risk. On Mars, cancer would not be a possibility, it would be a certainty. But cancer is a slow killer, taking years or decades to develop. Radiation on Mars offers more immediate consequences. High doses damage the central nervous system, leading to cognitive decline. Memory falters, reaction times slow, decision-making becomes impaired. Astronauts exposed to cosmic rays during simulated deep space missions show measurable deficits in problem-solving and motor skills. On a planet where survival depends on precise thinking and flawless execution, cognitive decline is not just a health problem, it is a death sentence. The eyes are particularly vulnerable. Cosmic rays strike the retina, creating flashes of light even when the eyes are closed. Over months and years, radiation causes cataracts, clouding the lens and eventually leading to blindness. The cardiovascular system also suffers. Radiation damages the lining of blood vessels, accelerating atherosclerosis and increasing the risk of heart attacks and strokes. A colonist on Mars would age faster than their counterparts on Earth, their body deteriorating under the constant assault of particles born in the deaths of distant stars. Then there are solar storms. The sun is not a stable, predictable star. It erupts. Massive coronal mass ejections hurl billions of tons of charged particles into space, travelling at millions of miles per hour. On Earth, these storms produce beautiful auroras, harmless light shows dancing across polar skies. On Mars, they are catastrophic. A solar storm striking Mars delivers radiation doses high enough to cause acute radiation sickness within hours. Nausea, vomiting, hair loss, and immune system collapse follow. Without immediate shelter, exposure during a major solar event would be fatal. The problem is warning time. On Earth, satellites monitor the sun constantly, providing hours or even days of advance notice before a solar storm arrives. On Mars, that infrastructure does not exist. Communication delays between Earth and Mars range from 4 to 24 minutes depending on orbital positions. By the time a warning is sent from Earth, the The storm may have already arrived. Colonists would need to detect solar eruptions themselves, using local monitoring systems, and retreat to shielded habitats within minutes. Any delay, any hesitation, and they would be caught in the open, defenseless beneath a sky turned lethal. The most commonly proposed solution is to build underground. If the surface is uninhabitable, then humanity will burrow beneath it, constructing habitats shielded by meters of Martian soil. Regolith, the loose rocky material covering Mars, can absorb much of the incoming radiation. A habitat buried under 3 meters of regolith would reduce radiation exposure to levels comparable to low Earth orbit, still far higher than Earth's surface, but potentially survivable for limited periods. Yet this solution is not simple, it is not elegant, it is a surrender. To live underground is to abandon the dream of walking freely beneath Martian skies, of standing on red dunes and watching twin moons rise. It is to accept a life of confinement, of artificial light, of walls pressing in on all sides. The psychological toll of such existence is profound. Studies of isolated environments on Earth, Antarctic research stations, submarines, long-duration space missions reveal that confinement breeds depression, anxiety, and interpersonal conflict. On Mars, there would be no relief, no open sky, no horizons stretching to infinity, just tunnels, chambers, and the knowledge that stepping outside even for a moment means exposure to invisible death. Building underground habitats also requires resources, energy, and technology that do not yet exist at the necessary scale. Excavating tunnels on Mars means moving tons of regolith, using equipment that must function in low temperatures, low atmospheric pressure, and constant dust. Power systems must operate continuously to maintain life support, requiring either nuclear reactors or vast solar arrays. Every component must be transported from Earth or manufactured on Mars, a process that would take decades and cost trillions. The underground city is not a decade away. It is not 2 decades away. It is a fantasy projected onto a future we cannot yet reach. Even if we build these habitats, even if we shield ourselves with regolith and live like moles beneath the Martian surface, one problem remains unsolved: reproduction. Radiation does not only harm adults, it attacks the most vulnerable stages of human development, threatening the very possibility of a multi-generational colony. Radiation damages reproductive cells. In men, it reduces sperm count and increases mutations. In women, it damages eggs, which unlike sperm are not continuously produced but are present from birth. A woman born on Mars or who spends years there would carry eggs irradiated throughout her lifetime. The risk of miscarriage, birth defects, and genetic abnormalities would skyrocket. Fetuses are even more vulnerable. During development, cells divide rapidly, and radiation-induced damage multiplies with each division. A pregnancy on Mars would be a genetic gamble, with outcomes impossible to predict. Animal studies offer grim insights. Mice exposed to cosmic ray simulations show reduced fertility, higher rates of fetal abnormalities, and offspring with cognitive impairments. While humans are not mice, the biological mechanisms are similar, enough to warrant caution. No human has ever been conceived, gestated, or born in deep space or on another planet. We simply do not know if it is possible, and the consequences of failure are not academic. They are the end of the colony. Proposed solutions to the radiation problem often invoke future technologies. Artificial magnetospheres, massive electromagnetic shields positioned at Mars's Lagrange point to deflect solar wind. Advanced materials, hydrogen-rich polymers or water-lined walls that absorb radiation more effectively than metal, pharmaceutical interventions, drugs that enhance DNA repair or protect cells from oxidative damage, genetic engineering, modifying human biology to increase radiation resistance. These ideas are not impossible, they're simply not imminent. Creating an artificial magnetosphere for an entire planet would require energy outputs and engineering capabilities far beyond our current reach. It would be one of the largest infrastructure projects ever conceived, dwarfing anything humanity has built. Even optimistic estimates place such technology decades away, and more realistic assessments suggest centuries. Advanced shielding materials exist in laboratories, but scaling them for use in habitats, spacecraft and spacesuits remains prohibitively expensive. Pharmaceutical and genetic solutions face ethical, regulatory and biological hurdles that cannot be overcome quickly. We are generations away from engineering humans capable of surviving Mars unshielded, and even if we could, should we? To alter human biology so fundamentally is to ask whether the beings living on Mars would still be human in any meaningful sense. The radiation nightmare is not a problem with a single solution. It is a cascade of interconnected challenges, each requiring breakthroughs in science, engineering and medicine. It is a reminder that Mars, despite its proximity and apparent familiarity, is profoundly alien. The red planet does not welcome life. It tolerates none. Its surface is a graveyard, sterilized by radiation over billions of years, and it will remain so unless we can bend physics, biology and economics to our will. To travel to Mars is to accept that every breath, every heartbeat, every moment spent there is borrowed time. The radiation does not pause. It does not forgive. It accumulates, invisible and patient, writing its damage into the cells of every living thing. And in the silence of that ancient airless world, beneath a sky that glows faintly with cosmic fire, the dream of colonization confronts its most implacable enemy. Not distance, not cost, but the universe itself, indifferent and unyielding, reminding us that some places were never meant for life. Stand on Earth and take a breath. Feel your lungs fill with nitrogen, oxygen, trace elements that have sustained life for billions of years. The air is invisible, effortless, abundant. We think nothing of it because it simply is. Now imagine standing on the surface of Mars. Your lungs expand, searching for oxygen, but there is none. Not in any meaningful quantity. The atmosphere around you is not just thin, it is almost absent. A whisper where there should be a symphony. And what little exists cannot sustain you for even a single breath. This is not an engineering challenge. This is a fundamental incompatibility between human biology and planetary reality. Mars's atmosphere is composed of approximately 95% carbon dioxide. The oxygen that keeps us alive, it exists at just 0.13%, not 13%, not 1%, 3%, 0.13%. To put this in perspective, if you were to somehow remove your helmet on Mars and attempt to breathe, you would not die from carbon dioxide poisoning first. You would die from the absence of oxygen. Your blood would stop carrying the fuel your cells need within seconds. Consciousness would fade in less than 15 seconds. Brain damage would begin almost immediately. Death would follow in minutes, though you would be unconscious long before then. But the composition is only part of the nightmare. The atmospheric pressure on Mars is less than 1% of Earth's. On average, it measures about 600 pascals, compared to Earth's 101,000 pascals at sea level. This is not merely thin air. This is effectively a vacuum. At this pressure, water cannot exist in liquid form. It either freezes solid or evaporates instantly into gas. Human blood at body temperature would begin to boil, not from heat, but from the absence of pressure. This phenomenon, known as ebulism, would cause the water in your soft tissues to vaporize. Your body would swell. Your eyes, your tongue, the moisture in your lungs, all would begin to boil away. This is the atmosphere problem, not inconvenient, not difficult, fundamentally hostile to human existence. The standard response to this reality is technological optimism. We will simply generate oxygen. We will build habitats. We will engineer our way around the problem. But this optimism dissolves when confronted with the actual requirements, the energy demands, the infrastructure needed, and the unavoidable physics that govern survival. Generating oxygen on Mars is possible in theory. The most discussed method is extracting it from the carbon dioxide atmosphere through a process called electrolysis, specifically splitting CO2 into carbon monoxide and oxygen. NASA's MOXIE experiment aboard the Perseverance rover has demonstrated this on a small scale, producing about 10 grams of oxygen per hour. 10 grams. A single human needs approximately 800 grams of oxygen per day just to survive at rest. To produce enough oxygen for one person, you would need 80 MOXIE units running continuously, consuming enormous amounts of electrical power. And MOXIE is a technology demonstration, not a life support system. Scaling it up requires not just more units, but massive energy infrastructure, reliable power generation in an environment where solar panels are perpetually covered in dust, where temperatures plunge to -80 degrees Fahrenheit at night, where no wind exists to provide alternative energy, and where nuclear reactors would need to be transported, assembled, and maintained millions of miles from the nearest replacement part. The energy problem is inescapable. Every breath you take on Mars must be manufactured. Every litre of oxygen must be extracted, filtered, pressurized, and delivered through systems that cannot fail even once. A single malfunction means asphyxiation, and all of this requires power. Constant, uninterrupted, reliable power. Solar panels degrade. Batteries lose capacity in extreme cold. Nuclear reactors require fuel, maintenance, and eventual replacement. There is no grid to fall back on, no emergency services, no backup infrastructure beyond what you brought with you. Even if oxygen generation could be solved, you cannot simply breathe oxygen into the Martian atmosphere and survive. You need pressure. You need an enclosed, sealed environment that maintains Earth-like atmospheric conditions. This brings us to the next nightmare: pressurized habitats. A habitat on Mars must maintain an internal pressure roughly 140 times greater than the external environment. This differential is enormous. Every square inch of the habitat's walls experiences significant outward force, constantly pushing against the structure, seeking any weakness, any microscopic flaw. Over time, materials fatigue, seals degrade, microfractures propagate, and on Mars there is no forgiveness. A single puncture, even a small one, initiates rapid decompression. The air inside rushes out through the breach, and if the hole is large enough or cannot be sealed quickly, the habitat depressurizes entirely. Anyone inside would experience the same fate as someone exposed to the Martian atmosphere directly. Consciousness lost within seconds, death within minutes. The only defense is redundancy, multiple sealed chambers, airlocks, emergency pressure suits always within reach. But redundancy adds mass, complexity, and points of failure. The materials required to build such habitats do not exist on Mars. They must be transported from Earth at extraordinary cost. Every kilogram launched into space costs thousands of dollars. A single habitat module capable of supporting a small crew would weigh tons, requiring multiple launches, assembly in orbit or on the surface, and constant maintenance once operational. And these habitats are not permanent. They are temporary shelters, subject to the relentless forces of thermal expansion, radiation damage, and the corrosive effects of Martian dust. Dust. The word seems benign, almost trivial. On Mars, it is a pervasive, insidious threat. Martian dust is not like Earth's dust. It is ultrafine, electrostatically charged, and composed of particles smaller than flour. It clings to everything. It infiltrates seals, clogs, filters, abrases moving parts, and cannot be easily removed. During dust storms, which can last for months and cover the entire planet, solar panels become useless, buried under layers of particulate that block sunlight. Equipment exposed to the elements degrades rapidly, and if dust enters a habitat through an airlock, it becomes an inhalation hazard. Martian dust is not just irritating, it is toxic. It contains perchlorates, highly reactive chemicals that are poisonous to humans. Inhaling Martian dust could cause respiratory damage, chemical burns to lung tissue, and long-term health effects we can only begin to guess at. Every time someone enters or exits a habitat, they bring dust with them. Every surface must be cleaned, every filter must be replaced. The cumulative effect is a maintenance burden that never ends, and yet, all of this, oxygen generation, pressurized habitats, dust mitigation, is only the beginning. These systems require not just energy, but materials, spare parts, technical expertise, and time. Time to repair, time to maintain, time that is stolen from scientific work, from exploration, from anything productive. Survival itself becomes a full-time occupation. This brings us to the fantasy of terraforming, the idea that Mars could be transformed into an Earth-like world over time. It is a concept that captures the imagination, a vision of green valleys and blue skies on a reborn planet. But it is a fantasy disconnected from physical reality. Terraforming Mars would require increasing its atmospheric pressure by a factor of at least 140, releasing enough gas to create a breathable atmosphere across an entire planet. Where would this gas come from? The most commonly proposed method is to release carbon dioxide trapped in Mars's polar ice caps and subsurface reservoirs by warming the planet. Even if every molecule of CO2 on Mars were released into the atmosphere, studies suggest it would only increase atmospheric pressure to about 7% of Earth's, still far too low to support human life without pressure suits. But even if enough gas could be found, there is a deeper problem. Mars cannot hold on to an atmosphere over geological timescales. It lacks a global magnetic field. Earth's magnetic field shields our atmosphere from the solar wind, a stream of charged particles constantly flowing from the sun. Without this shield, the solar wind strips away atmospheric particles, molecule by molecule, year after year. This is what happened to Mars's original atmosphere billions of years ago. It was lost to space. Any attempt to give Mars a thick atmosphere would face the same fate. Over thousands or tens of thousands of years, the solar wind would erode it away. Unless a planetary magnetic field could somehow be artificially generated, which is beyond any conceivable technology, a terraformed Mars would be temporary. The atmosphere would bleed into space, and the planet would return to its current state. Gravity compounds the problem. Mars's gravity is only 38% of Earth's. Lower gravity means atmospheric particles have higher velocities at the same temperature, making it easier for them to reach escape velocity and leave the planet entirely. This is another reason Mars lost its atmosphere, and why holding onto a new one would be nearly impossible. The timescales involved are staggering. Even the most optimistic terraforming proposals suggest it would take thousands of years, possibly tens of thousands, to alter Mars's atmosphere, temperature and surface conditions to something approaching habitability. And this assumes we possess technologies that do not yet exist and may never exist. Planetary-scale engineering, sustained energy output equivalent to the entire industrial capacity of Earth, directed solely at Mars for millennia. This is not a project. It is a multi-generational, perhaps multi-civilization commitment, one that assumes political stability, economic continuity, and technological progress without interruption for longer than recorded human history. It is not realistic. It is mythology dressed in scientific language. Meanwhile, proponents of Mars colonization often invoke ISRU, in situ resource utilization, the concept of living off the land, extracting water, oxygen, and building materials from Martian resources. On paper, ISRU sounds elegant. Why transport everything from Earth when Mars has ice, minerals, and carbon dioxide? But the reality is far more complex. Extracting water ice from Martian soil requires mining equipment, energy for heating, and purification systems. Martian ice is not pure. It is mixed with soil, perchlorets, and other contaminants. Processing it into drinkable water demands infrastructure that itself must be built, maintained, and powered. Extracting metals and building materials from Martian regolith requires smelting, refining, and manufacturing capabilities that do not exist on Mars and cannot be easily replicated. ISRU is not a shortcut. It is an additional layer of industrial complexity that must be bootstrapped from scratch in one of the most hostile environments imaginable. Every component needed to make ISRU work must first be transported from Earth. Every ton of equipment sent to Mars to enable resource extraction is a ton that could have been used for life support, habitats, or supplies. The trade-off is not obvious. In many scenarios, it is more efficient to simply bring what you need from Earth rather than attempting to manufacture it on Mars. The atmosphere problem is not one problem. It is a cascade of interconnected challenges, each demanding solutions that strain the limits of current technology and economics. You cannot breathe money. You cannot purchase an atmosphere. You cannot engineer away the fundamental incompatibility between human physiology and Martian conditions without accepting that every moment of survival depends on systems that must never fail in an environment that offers no second chances. The air we breathe on Earth is not a luxury. It is not a convenience. It is the baseline requirement for life, a condition so fundamental that we forget it exists until we imagine a world where it does not. Mars is that world, a world where every breath is manufactured, every pressure seal is a point of failure, and every day is a gamble against the slow, grinding certainty that complex systems eventually break down. To colonize Mars is to accept that the atmosphere itself is your enemy, not a challenge to overcome, but a permanent, unrelenting hostility that can only be temporarily held at bay. And in that realization, the dream of a thriving Martian civilization begins to dissolve, replaced by the cold, unforgiving truth. You cannot colonize a planet where the very air conspires against your existence. Mars pulls at you with only 38% of Earth's strength. It sounds like a minor detail, a footnote in the colonization story. But this seemingly small number is a biological catastrophe waiting to unfold. Gravity is not merely the force that keeps our feet on the ground, it is the architect of our entire physiology, the invisible sculptor that has shaped every bone, every muscle, every heartbeat over millions of years of evolution. On Mars, that ancient partnership between body and planet dissolves. What remains is a human form struggling against an environment it was never designed to inhabit. And unlike radiation or atmosphere, gravity cannot be shielded against, filtered out, or engineered away. It simply is, or rather, it simply isn't. When we imagine Mars colonists, we picture them walking across rust-coloured plains, working in habitats, building civilization under alien skies. What we don't picture is what happens inside their bodies with each passing month. From the moment a human sets foot on Mars, their skeleton begins to dissolve. On Earth, our bones constantly rebuild themselves in response to the stress of gravity. Every step, every movement, every moment of standing sends signals to bone cells, telling them to maintain their density and strength. Remove that gravitational stress, and the body interprets it as a signal that bones are no longer needed. In microgravity, astronauts lose approximately 1 to 2% of bone mass per month in weight-bearing bones. On Mars, with its 38% gravity, the loss would be slower but still relentless. Current estimates suggest colonists would lose bone density at perhaps 0.5 to 1% per month, a rate that would leave their skeletons dangerously fragile within a few years. The bones most affected are those that bear weight on Earth: the spine, hips, and legs. These structures, which evolved to support us against Earth's pull, begin to thin and weaken. The calcium that once reinforced them leaches into the bloodstream, creating a cascade of secondary problems. Elevated calcium levels can lead to kidney stones, a painful and potentially life-threatening condition in an environment where medical facilities are limited, and evacuation to Earth takes months. The irony is stark. The very substance that gives bones their strength becomes a poison when released in excess, circulating through the body with nowhere to go. But bone loss is only the beginning. Muscles, too, begin to atrophy in Mars's weak gravity. Every muscle in the human body evolved to work against Earth's gravitational constant. The heart, a muscle designed to pump blood upward against gravity's pull, suddenly finds its job far easier on Mars. This sounds beneficial, but it is anything but. Without the constant resistance that Earth's gravity provides, the heart begins to weaken. It becomes smaller, less efficient, its muscle fibers thinning like unused cables. Cardiovascular deconditioning sets in, a process where the entire circulatory system adapts to the lower demands of a low-gravity environment. Blood vessels lose their tone. The body reduces its overall blood volume, deciding it no longer needs as much fluid circulating through a system that faces minimal gravitational resistance. On Earth, when you stand up, gravity pulls blood downward into your legs. Your cardiovascular system immediately compensates, constricting blood vessels and accelerating your heart rate to ensure blood continues flowing to your brain. On Mars, this response begins to fade. The body forgets how to fight gravity because there is so little gravity to fight. Colonists would experience chronic orthostatic intolerance, dizziness, and fainting when changing positions, their bodies unable to regulate blood pressure effectively. Simple actions, standing up from a chair, climbing stairs, would become exercises in maintaining consciousness. The skeletal muscles fare no better. Without Earth's constant gravitational load, muscles shrink. Leg muscles, which on Earth must support our entire body weight with every step, find themselves working against a fraction of that load on Mars. The result is predictable: Atrophy. Muscles lose mass and strength, not over years, but over months. Exercise can slow this process, and astronauts on the International Space Station spend hours each day working out to counteract muscle loss. But even rigorous exercise cannot fully compensate for the absence of gravity. The mechanical loading that comes from simply existing in Earth's gravitational field cannot be perfectly replicated by machines. On Mars, colonists would need to exercise constantly, perhaps several hours per day, just to maintain a fraction of their Earth strength, and even then they would be fighting a losing battle. Perhaps the most disturbing implication of Mars's low gravity is what it means for human reproduction and development. No human has ever been conceived, gestated, or born in reduced gravity. We have no data, no experiments, no understanding of whether it is even possible. On Earth, gravity plays a crucial role in fetal development. Fluid dynamics within the womb, the formation of the skeletal system, the development of muscles and organs all occur within the context of 1G. What happens when that context is reduced to 0? 30G? We simply do not know. But the possibilities are deeply troubling. Bone development in a fetus occurs in response to mechanical stress. If that stress is reduced, will the skeleton form properly? Will bones be dense enough to support even Mars's reduced gravity? Or will children be born with skeletons too fragile to bear their own weight? Muscle development too depends on resistance and load. A child growing in Mars's gravity might develop muscles adequate for Mars but utterly insufficient for Earth. The implications extend beyond the physical. The vestibular system, the inner ear structures that govern balance and spatial orientation, calibrate themselves during early development based on gravitational input. Children born and raised on Mars might develop vestibular systems incompatible with Earth's gravity, making them permanently adapted to Mars and unable to ever visit the planet of their genetic heritage. Then there is the cardiovascular system. A child's heart and blood vessels develop in response to the demands of pumping blood against gravity. In Mars's weak gravity, would a developing cardiovascular system be adequate? Or would Martian-born children have hearts and circulatory systems too weak to function properly, even in their native environment? And if they could never return to Earth without their cardiovascular systems failing under the increased gravitational stress, what does that make them? Are they Martians, forever severed from humanity's homeworld, unable to walk where their ancestors walked? Even for adults, the implications of long-term Mars habitation are severe. After several years on Mars, colonists' bodies would have adapted so thoroughly to the reduced gravity that returning to Earth might be physiologically impossible. Their bones would be too brittle to support Earth's gravity, their muscles too weak, their hearts unable to pump blood effectively against the increased load. A colonist who spent 5 or 10 years on Mars might find that coming home would result in broken bones, torn muscles, cardiovascular collapse. They would be trapped, not by choice or circumstance, but by biology. Mars would not be a colony in the traditional sense. It would be a one-way biological transformation. The neurological effects of reduced gravity are equally concerning but less understood. The human brain evolved in a constant gravitational field. Fluid distribution in the skull, cerebrospinal fluid dynamics, even the way neurons fire, all occur within the context of Earth gravity. In space, astronauts experience fluid shifts toward the head, causing facial puffiness, sinus congestion, and increased intracranial pressure. This pressure can damage the optic nerve, causing vision problems that persist even after returning to Earth. On Mars, these effects would be less severe than in microgravity, but they would still occur. Chronic increased intracranial pressure could lead to long-term neurological damage, cognitive impairment, and vision loss that cannot be corrected. The vestibular system, which governs balance and spatial orientation, would also suffer. On Earth, this system is finely tuned to 1G. On Mars, it would need to recalibrate to 0, 8G. Initially, colonists would experience disorientation, dizziness, and difficulty with coordination. Over time, the brain would adapt, but this adaptation comes with a cost. The vestibular system would lose its Earth calibration. Colonists who spent years on Mars would find that returning to Earth would trigger severe vertigo, nausea, and balance problems. Their brains, now tuned to Mars, would interpret Earth's gravity as excessive, overwhelming, wrong. Then there is the immune system. Recent research has shown that microgravity impairs immune function, making astronauts more susceptible to infections and causing dormant viruses to reactivate. The mechanisms are complex, involving changes in gene expression, cellular function, and immune cell behavior. On Mars, with its reduced but not absent gravity, similar effects would likely occur, though to a lesser degree. Colonists would face an increased risk of infections in an environment where medical resources are scarce, and evacuation is measured in months. A simple infection that would be minor on Earth could become life-threatening on Mars, not because of the infection itself, but because the immune system is too compromised to fight it effectively. The most frustrating aspect of Mars's gravity problem is that there is no solution. On a spacecraft or space station, artificial gravity can theoretically be created through rotation. A spinning habitat generates centrifugal force that mimics gravity, allowing inhabitants to maintain bone density and muscle mass. But Mars is not a spacecraft. It is a planet, and planets do not rotate fast enough to generate meaningful artificial gravity. A colony on Mars's surface would be stuck with 0, 8G, period. There is no engineering solution, no technological fix. You cannot increase a planet's gravity without increasing its mass, and you cannot increase a planet's mass with any technology we possess or can even imagine. Some have proposed building rotating habitats on Mars's surface, cylindrical structures that spin to create artificial gravity inside. But this creates more problems than it solves. Such structures would be enormously expensive and complex to build. Colonists would spend part of their time in the spinning habitat experiencing artificial 1G and part of their time outside in Mars's natural 0G. The constant switching between gravitational environments would be physiologically stressful, requiring the body to continuously adapt and readapt, and it raises an absurd question. If colonists must spend most of their time inside spinning habitats to maintain their health, why are they on Mars at all? Why not simply build rotating habitats in space, where they would have the same benefits without the added dangers of Mars's radiation, toxic soil, and lack of atmosphere? The research gaps here are profound and troubling. All of our data on reduced gravity comes from either microgravity on the International Space Station or from brief stays on the Moon, which has 16% of Earth's gravity. We have no long-term data on human health at Mars's specific gravity level. We don't know if 0.38G is enough to prevent catastrophic bone loss, or if it merely slows it. We don't know if children can develop normally in that gravity, or if pregnancy is even viable. We have no data on whether the cardiovascular system can adapt to 0.38G without permanent damage, or whether the immune system can function adequately. These are not minor gaps in knowledge. They are chasms, black voids in our understanding that must be filled before any serious colonization attempt can be considered remotely ethical. And filling those gaps would require experiments that may not be possible. We cannot send pregnant women to Mars to see if their babies develop properly. We cannot subject children to years of reduced gravity to study the effects on their growth. The ethical barriers are insurmountable, and rightly so. But without that data, any Mars colony would be a biological experiment with human subjects, conducted in an environment where rescue is impossible, and the consequences of failure are measured in lives. Gravity is the silent betrayal at the heart of Mars colonization. It is not dramatic like radiation, or immediate like the lack of breathable air. It is slow, insidious, eroding health and capability year by year. It does not kill quickly. It transforms, weakens, traps. It takes strong, healthy humans and gradually turns them into fragile beings who can never go home, who may never be able to have healthy children, who must live with chronic pain, weakness, and medical complications for the rest of their lives. And there is no escape, no solution, no technology that can change the fundamental mass of a planet. Mars's gravity is what it is, and what it is incompatible with long-term human health. Mars shimmers in the imagination with promises of frozen oceans and ancient riverbeds. We are told water exists there, locked beneath the surface, waiting to sustain future colonies. But how long would it truly take to transform ice into life? And what would be the cost, not in dollars, but in energy, time, and hope? As we descend toward Mars in our mind's journey, we must confront a harsh reality. Water on Mars is not a resource. It is a challenge wrapped in ice, buried in darkness, and guarded by physics itself. The excitement began decades ago when orbital missions detected water ice at Mars's poles and evidence of subsurface ice scattered across the planet. Headlines proclaimed, "Mars had water," as if this singular fact would solve the riddle of colonization. But the reality is far more complex, far more unforgiving. Yes, water exists on Mars, but it exists in forms and locations that make it nearly inaccessible to human survival. It is not flowing in convenient rivers or pooling in accessible lakes. It is frozen solid, buried under layers of soil and dust, mixed with toxic perchlorates, and distributed across a planet where temperatures plunge to negative 80 degrees Fahrenheit on average. The poles of Mars contain vast deposits of water ice mixed with frozen carbon dioxide. These polar caps are beautiful, glittering white against the rusty red landscape, but they are also among the most inhospitable regions on the planet. Temperatures at the poles can drop below negative 200 degrees Fahrenheit during winter. No human settlement could survive there without constant, immense energy expenditure simply to prevent freezing to death. Even if we could build habitats at the poles, extracting water would require heavy mining equipment, all of which would need to be transported from Earth or manufactured on Mars, a problem we will return to shortly. Mid-latitude regions contain permafrost, layers of ice mixed with Martian soil just beneath the surface. Satellites have mapped these deposits with precision, revealing that water ice exists under perhaps 1/3 of the Martian surface. But this ice is not pure. It is contaminated with regolith, dust, and chemical compounds that would poison any human who drank it untreated. Extracting this ice would require drilling or excavation, breaking through frozen ground harder than concrete, then heating the mixture to separate water from soil. This process demands staggering amounts of energy that would need to come from solar panels operating under sunlight only 40-fold as intense as Earth's, or from nuclear reactors that would themselves need to be transported and maintained by a colony perpetually on the edge of survival. Even if water ice is successfully extracted, it must then be purified. Martian ice contains perchlorates, toxic salts that can damage human thyroid function and render water undrinkable. Removing these chemicals requires sophisticated filtration and chemical processing, technologies that are energy-intensive even on Earth, where resources are abundant. On Mars, every joule of energy spent purifying water is energy not spent heating habitats, growing food, or producing oxygen. The cost is not merely financial, it is existential. Let us imagine for a moment that a colony successfully extracts and purifies water. What then? Water on Mars must be kept liquid by force. The atmospheric pressure is so low that liquid water cannot exist naturally on the surface. It either freezes solid or evaporates instantly into vapor. This means all water must be stored in pressurized, heated containers. Any leak, any crack in a tank, any failure in a heating system, and the water is lost, not spilled, lost, evaporated into the thin Martian air, irrecoverable. On Earth, a broken water pipe is an inconvenience. On Mars, it could be a death sentence. Closed-loop life support systems, the kind necessary for any Mars colony, are extraordinarily fragile. These systems recycle water from every possible source, including urine, sweat, and exhaled moisture. On the International Space Station, such systems operate with remarkable efficiency, but even there water is gradually lost and must be resupplied from Earth. Small losses accumulate, a few litres here, a few there. Over months these losses become critical. On Mars there is no resupply ship arriving every few months. There is no safety net. If a colony's life support system loses just 1% of its water per month, it would need to extract and purify hundreds of litres from the Martian surface every single month just to break even. Miss a month, face an equipment failure, experience a dust storm that cuts solar power, and the colony begins to die of thirst. The psychological weight of such precarity cannot be overstated. Imagine living every day knowing that your survival depends on machines functioning flawlessly in an environment designed to destroy them. That every glass of water you drink was torn from frozen ground at immense cost. That a single system failure could leave you with nothing to drink within days. This is not science fiction. This is the engineering reality of water on Mars. But water is only the beginning of the resource problem. A human colony requires far more than water to survive. It requires nitrogen, essential for plant growth and for creating breathable air mixtures. Earth's atmosphere is 78% nitrogen. Mars's atmosphere is less than 3% nitrogen, and what little exists is dispersed across an entire planet in an atmosphere 1/100th the density of Earth's. Extracting nitrogen from the Martian atmosphere would require compressing and processing vast quantities of air, again demanding enormous energy inputs. Without nitrogen, plants cannot grow. Without plants, there is no food, no oxygen production, no hope of self-sufficiency. Consider also the rare elements necessary for technology. Electronics require rare earth metals. Batteries require lithium and cobalt. Medicine requires chemical precursors and complex compounds. While Mars likely contains these elements somewhere in its crust, we do not know where, in what concentrations, or how difficult they would be to extract. On Earth, mining operations employ thousands of workers, massive machinery, and complex logistics networks. On Mars, a colony of even 1,000 people would have no ability to replicate such operations. they would be entirely dependent on the equipment they brought with them. And when that equipment fails, as all equipment eventually does, there will be no replacements. Fuel for return journeys presents yet another impossibility. Bringing enough rocket fuel from Earth to launch a return mission is impractical due to mass constraints. The proposed solution is to manufacture fuel on Mars using the Sabatier reaction to combine hydrogen with carbon dioxide from the atmosphere, producing methane and water. But this process requires enormous amounts of hydrogen, which must either be brought from Earth or extracted from Martian water, bringing us back to the water problem. It also requires reliable power, sophisticated chemical equipment, and flawless execution over months or years. A single failure in fuel production could strand colonists permanently, transforming a settlement into a tomb. Perhaps the most devastating resource challenge is food. The dream of Martian agriculture is seductive. Greenhouses filled with crops, grown in Martian soil, fed by Martian water, illuminated by Martian sunlight. But this dream dissolves under scrutiny. Martian soil is not soil in any meaningful sense. It is regolith, a toxic dust filled with perchlorates and lacking the organic matter necessary for plant growth. Before a single seed could be planted, Martian regolith would need to be detoxified, enriched with nutrients, and mixed with organic material, none of which exists on Mars. Every ounce of fertilizer, every microbe necessary to create living soil would need to be brought from Earth. Water scarcity makes agriculture even more daunting. Crops require consistent watering. A single human needs roughly half a ton of food per year. Growing that food requires thousands of litres of water. Multiply that by even a small colony, and the water demands become staggering. Remember, every drop of that water must be extracted from frozen ground, purified, heated and maintained in liquid form. The energy cost alone would consume a significant fraction of the colony's total power generation. Sunlight on Mars is weak and inconsistent. During dust storms, which can last weeks or months, sunlight is reduced to a dim twilight. Plants require specific wavelengths of light to photosynthesize, meaning Martian greenhouses would need supplemental grow lights operating continuously. These lights would consume enormous amounts of electricity that could otherwise be used for heating, water extraction, or life support. The energy budget of a Mars colony is a zero-sum game. Every watt spent growing food is a watt not spent keeping people alive. The space required for agriculture is equally prohibitive. A single human requires roughly 50 square meters of growing space to produce enough food to survive, assuming perfect efficiency and no crop failures. A colony of 100 people would need a greenhouse covering 5,000 square meters, all of it pressurized, heated, and illuminated. The structural materials alone would weigh hundreds of tons, far beyond the payload capacity of any current or proposed spacecraft. And this assumes nothing goes wrong. No diseases, no pests, no equipment failures, no human errors. In reality, crop failures are common even on Earth, where conditions are ideal and support systems are abundant. On Mars, a single crop failure could mean starvation. Some propose resupply missions from Earth, cargo ships arriving periodically with food, water, medicine, and equipment. But the economics and logistics of such missions are nightmarish. Launching payloads to Mars costs tens of thousands of dollars per kilogram. A single resupply mission carrying enough food and water for a year would cost billions of dollars. And missions to Mars can only launch during specific alignment windows, which occur roughly every 26 months. Miss a launch window due to technical problems, budget shortfalls, or political changes, and the colony faces 2 years without resupply. 2 years of dwindling resources, rationing, and desperation. The notion that Earth could reliably support a Mars colony with regular shipments is a fantasy built on optimism and ignorance of orbital mechanics. The manufacturing problem seals the impossibility. Modern technology depends on supply chains spanning the entire globe. A single smartphone contains materials from dozens of countries, assembled in factories employing thousands of workers. On Mars, there would be no factories, no supply chains, no workforce. Colonists would be entirely dependent on the tools they brought with them. When a solar panel degrades, when a water pump fails, when a pressure seal cracks, there would be no replacement parts. They could not manufacture a new computer chip, a new electric motor, or even a simple valve. The complexity of modern manufacturing is so immense that even small nations on Earth cannot produce everything they need. A Mars colony would be infinitely more isolated, more vulnerable, more dependent. This dependence would be permanent. There is no path to self-sufficiency. Mars lacks the population, the infrastructure, the raw materials, and the energy abundance necessary to replicate even a fraction of Earth's industrial capacity. A colony would remain forever tethered to Earth, a satellite in both the literal and economic sense. And should Earth ever lose interest, face its own crises, or simply decide the cost is too great, the colony would be abandoned. Left to manage declining equipment with no hope of replacement. A slow extinction watched from 140 million miles away. The water myth, the promise that Mars's ice will sustain us, is perhaps the cruelest deception of all, because it is not entirely false. Water is there, it exists. But existing and being accessible are vastly different things. Water on Mars is locked behind barriers of temperature, chemistry, energy, and engineering so formidable that extracting it becomes an endless war against entropy itself. And in that war, entropy always wins. As we contemplate these realities, floating in thought above the frozen Martian surface, we must ask ourselves difficult questions. What does it mean to survive on a world that offers nothing freely? What is the cost of transforming ice into water, regolith into soil, darkness into light? And is survival, mere persistence in the face of overwhelming hostility, the same as living? The resources of Mars are not treasures waiting to be claimed. They are illusions, mirages that shimmer with possibility but dissolve upon approach. The water is there, yes, but it might as well be on another world entirely. For in practical terms, in the terms that matter to human survival, it is. Beyond the engineering challenges, beyond the radiation and the thin atmosphere, lies a barrier far more insidious, one that cannot be solved with better technology or more funding. It is the human mind itself. For all our dreams of Martian cities and interplanetary civilization, we must confront an uncomfortable truth. Humans are not designed for permanent isolation. Our psychology, our social structures, our very consciousness evolved on Earth, shaped by millions of years of open skies, natural cycles, and communities that could grow, change, and escape when necessary. Mars offers none of this. To colonize Mars is not merely to transport bodies across space. It is to confine the human spirit in ways we are only beginning to understand. Imagine waking each day in the same underground bunker, breathing the same recycled air, seeing the same faces, knowing that this room, this tunnel, this life is all there will ever be. There is no elsewhere, no other city to move to, no different climate to escape to, no fresh community to join. On Earth, When life becomes unbearable, we have options. We can relocate, start over, seek change. On Mars, there is only the colony. And the colony is a cage, however well-intentioned its design. The psychological effects of isolation are not theoretical. They have been documented extensively in Antarctic research stations, submarines, space stations, and long-duration missions. In these environments, humans experience profound mental strain even when they know rescue is possible, even when they can see Earth from their windows, even when their isolation will end in months rather than years. On Mars, there would be no such comfort. Communication with Earth would suffer delays of up to 24 minutes each way, making real-time conversation impossible. A colonist experiencing a mental health crisis could not call a therapist, could not speak to a loved one, could not hear a reassuring voice when darkness closes in. They would have only recordings, text messages received hours after being sent, and the knowledge that everyone they left behind is living full lives on a world they will never see again. The human mind craves novelty, nature, and the unexpected rhythms of a living world. On Earth, even in cities, we are surrounded by change. Weather shifts, seasons turn, birds migrate, trees bloom and shed their leaves. These cycles are not trivial. They anchor our psychology in time, remind us that we are part of something larger, something alive. Mars has no seasons in any meaningful sense. Its sky is a perpetual rust-coloured haze. Its landscape never changes except when dust storms erase visibility entirely. There are no forests to walk through, no oceans to gaze upon, no rain to listen to at night. Every sound will be artificial, every vista barren, every moment a reminder of absence. In confined spaces, human behaviour deteriorates in predictable ways. Small irritations become major conflicts. Personality clashes that might be manageable on Earth become unbearable when escape is impossible. Antarctic winter overcrews, isolated for months in research stations, report depression, hostility, insomnia, and what psychologists call the long eye, a 1,000-yard stare born of monotony and confinement. These are people who chose their mission, who were extensively screened, who knew their isolation would end. Now imagine the same conditions, but permanent, with no rescue, no rotation, and the certain knowledge that this is not a mission, but a life sentence. Social dynamics in a Mars colony would fracture under stresses Earth societies rarely face. On Earth, governance relies on the assumption that people can leave. Laws are enforced not just by threat, but by the implicit understanding that staying in a society is a choice. On Mars, there would be nowhere to go. If conflict arises, if leadership becomes authoritarian, if injustice takes root, colonists would have no escape. They could not defect. They could not seek asylum. They would have only each other, locked in a closed system where every relationship is permanent and every mistake reverberates through the entire community. Who would govern such a place? What legal system would apply? If someone commits a crime, there are no prisons to send them to, no neighbouring jurisdictions to request aid from. Exile means death. Confinement means draining resources the colony cannot spare. Justice would become a matter of survival calculus, not ethics. And what of dissent? On Earth, dissatisfied citizens can protest, vote with their feet, or form alternative communities. On Mars, dissent would be existential risk. A divided colony is a dying colony. Unity would be enforced not by choice, but by necessity. Freedom would be sacrificed at the altar of survival. Then there is the question of reproduction, perhaps the most ethically troubling aspect of Martian colonization. For a colony to be self-sustaining, children must be born. But a child born on Mars would face a fate no human has ever endured. They would grow up in artificial light, breathing recycled air, never feeling rain, never seeing a forest, never swimming in an ocean, never running freely under an open sky. They would know Earth only through videos and stories, a mythical paradise they could never visit. Their bones, adapted to Mars' 38% gravity, would be too weak to support them on Earth. Their cardiovascular systems would fail under Earth's atmospheric pressure. These children would be born into exile, unable to ever walk the world their parents came from. They would be the first generation of humanity permanently severed from their evolutionary home. What right do we have to make that choice for them? A Martian-born child would have no option, no agency, no ability to consent to their fate. They would be imprisoned by biology, condemned to a world they did not choose, denied the full human experience their parents once knew. This is not colonization. It is genetic exile. It raises questions so profound they challenge the moral foundation of the entire endeavor. Is it ethical to create a generation of humans who will never know what it means to be fully human, to walk freely on a living world, to experience the environment that shaped every generation before them? The mental health crisis that would inevitably arise in such a colony would be unlike anything humanity has faced. Depression, anxiety, and psychosis are already epidemic on Earth, where we have nature, sunlight, open spaces, and robust mental health systems. On Mars, these conditions would intensify, compounded by isolation, confinement, and the relentless stress of survival. And yet, Mars would have no psychiatric hospitals, no therapists on every corner, no pharmaceutical supply chains capable of producing the medications that millions rely on. A colonist experiencing severe depression or psychosis would have limited treatment options and no escape from the environment causing their distress. In extreme cases, they could become a danger to themselves or others, threatening the survival of the entire colony. The harsh reality is that mental health resources would be minimal, and those struggling would be expected to simply endure or be left behind in ways we would find unthinkable on Earth. Cultural and intellectual stagnation would follow inevitably. Human civilization thrives on diversity of thought, cross-pollination of ideas, and the continuous influx of new perspectives. A Mars colony, even at its largest projected size, would number in the hundreds or low thousands for generations. This is not a civilization. It is a village. And villages, when isolated, do not innovate. They ossify. Art, music, literature, philosophy. All these require a critical mass of people, a diversity of experiences, and the freedom to experiment. On Mars, resources would be so constrained, survival so precarious, that creative endeavors would be seen as luxuries the colony could not afford. Education would be utilitarian, focused on engineering and survival skills. Entertainment would be limited to whatever could be transmitted from Earth or produced locally with minimal resources. The richness of human culture, the festivals, the spontaneous gatherings, the serendipitous encounters that spark new ideas, all of this would be absent. Even the genetic diversity necessary for a healthy population would be lacking. A founding population of a few hundred people would face severe genetic bottlenecking, leading to increased rates of hereditary diseases and reduced immunity to new pathogens. On Earth, populations intermix constantly, ensuring genetic vigor. On Mars, the gene pool would stagnate, and within a few generations the biological consequences would become unavoidable. Intermarriage among a small population would be inevitable, increasing the risk of genetic disorders and reducing the population's overall resilience. This is not speculation, it is basic population genetics, a problem that has plagued isolated human communities throughout history. History offers sobering lessons about isolated communities. The Roanoke colony vanished. The Donner Party resorted to cannibalism. Antarctic research stations require constant resupply and crew rotations to prevent psychological collapse. Even Earth's most remote inhabited places, islands, Arctic outposts, desert settlements, survive only because they are connected to the outside world. They receive supplies, new people, medical evacuations, and most importantly, the option to leave. Remove that connection, and these communities would fail within years. Mars would be the most extreme isolation experiment ever attempted, and unlike any historical precedent, its inhabitants could not leave. Ships from Earth would take months to arrive, far too long for medical emergencies, psychological crises, or unforeseen disasters. If a critical system failed, if a disease outbreak occurred, if social cohesion collapsed, there would be no rescue. The colony would be on its own, with no fallback, no safety net, no possibility of evacuation. Then there is the question of motivation. Why would people stay? The initial settlers might be driven by idealism, adventure, or the desire to be part of history. But after the novelty fades, after years of hardship with no improvement in sight, after watching friends suffer and die from radiation exposure or accidents, after realizing that life will never be comfortable, that children will never play outside, that every day is a struggle against an environment trying to kill you, why would anyone choose to remain? On Earth, even in difficult circumstances, there is hope for improvement, for change, for something better for the horizon. On Mars, there is only Mars. The conditions will not improve. The environment will not become more forgiving. The colony will not transform into a paradise. It will always be a survival scenario, generation after generation, with no end in sight. The propaganda surrounding Mars colonization often depicts happy families in spacious habitats, children playing in gardens under domed skies, a thriving society building a new world. This is fantasy. The reality would be cramped corridors, recycled air, rationed food, constant equipment failures, and the ever-present knowledge that one mistake, one malfunction, one moment of carelessness could kill everyone. It would be a life defined by fear, scarcity, and confinement. And unlike explorers or researchers who endure hardship for a limited time, Mars colonists would endure it forever, knowing their children and grandchildren would inherit the same struggle. The social fabric of such a community would be fragile, held together not by shared values or cultural bonds, but by the simple fact that mutual cooperation is the only path to survival. But history shows that survival alone is not enough to sustain human societies. We need meaning, purpose, beauty, freedom, and hope. Mars offers none of these in abundance. It offers only the grim satisfaction of having survived another day. In the end, the psychological and social impossibility of Mars colonization may be the most insurmountable barrier of all. We can theoretically solve engineering problems with enough time and resources. We can perhaps mitigate radiation with better shielding. We might even develop technologies to produce breathable air and water. But we cannot re-engineer the human psyche. We cannot erase millions of years of evolution that shaped us for life on Earth. We cannot make people thrive in environments that strip away everything that makes life worth living. To colonize Mars is to ask humans to become something they are not, to endure conditions no previous generation has faced, to sacrifice freedoms and experiences that define what it means to be human. It is to create a society of exiles who can never go home, raising children who will never know what home truly means, and for what, to prove it can be done, to satisfy the ambitions of billionaires and the fantasies of science fiction, to escape the problems of Earth by fleeing to a place 1,000 times more hostile. The dream of Mars is beautiful, but dreams must eventually face the harsh light of reality. And the reality is that we are not ready, not technologically, not biologically, and certainly not psychologically. We are creatures of Earth, bound to this world not just by gravity, but by every aspect of our being. To leave it permanently is not an act of exploration. It is an act of exile, and exile, no matter how voluntary, is a form of suffering. Mars may call to us across the void, but the cost of answering that call may be greater than we are willing or able to pay. In the silence of space, numbers do not lie. They whisper truths that enthusiasm cannot drown out. As we turn our gaze from the distant ice giants back toward the red glow of Mars, we must confront not the poetry of exploration, but the mathematics of survival. Dreams are built on wonder. Civilizations are built on resources, engineering, and economic reality. And when we examine Mars through this lens, the vision begins to fracture, revealing cracks that no amount of optimism can seal. The cost of establishing even the most basic human presence on Mars is staggering beyond comprehension. Current estimates suggest that initial infrastructure alone would require investments exceeding $1 trillion. This is not the cost of a thriving colony. This is merely the price of arrival, of constructing habitats that could sustain perhaps a few dozen people for a few years. For context, the International Space Station, humanity's most expensive engineering project, cost roughly $150 billion over decades and houses only 6 to 7 people at a time in low Earth orbit, just 250 miles above our heads. Mars is not 250 miles away. It is 140 million miles distant, separated from us by months of travel, infinite vacuum, and lethal radiation. Every dollar spent on Mars colonization must be justified not by romantic visions of frontier spirit, but by tangible returns. And here, the economic case collapses entirely. Mars has nothing to offer Earth. No resource exists on the red planet that would justify the cost of extraction and transport across interplanetary space. Rare metals? They exist in abundance in asteroids far closer to Earth. Water? We have oceans. Helium-3 for theoretical fusion reactors. The Moon offers easier access. Scientific knowledge? Robotic missions provide that at a fraction of the cost and without risking human lives. Some proponents speak of Mars as a backup for humanity, an insurance policy against extinction. But this logic crumbles under scrutiny. The cost of making Mars habitable for even a small population would far exceed the cost of preventing or recovering from nearly any catastrophe on Earth. If we possess the technology to terraform an entire dead planet, we certainly possess the technology to repair a damaged but still living one. Earth, even after nuclear war, asteroid impact or climate catastrophe, would remain more hospitable than Mars on its best day. The economics of planetary backup make no sense when one planet has breathable air, liquid water, and magnetosphere, and the other has none of these things. But let us move beyond cost and examine the engineering reality. Mars colonization requires not 1 or 2 functioning systems, but hundreds, each operating flawlessly for years without failure. Life support must recycle air and water with near-perfect efficiency. Power generation must function through dust storms that can last months and block out the sun. Food production must occur in artificial environments with no natural soil, no pollinators, no natural light cycles. Communications face a time delay of up to 24 minutes round trip, meaning no real-time assistance from Earth in emergencies. Every single component, from air filters to electronic circuits, must be manufactured on-site or brought from Earth at enormous cost. Redundancy, the foundation of all reliable engineering, becomes nearly impossible at the scale required for a permanent colony. On Earth, if a water treatment plant fails, we can truck in supplies, repair parts, or relocate people. On Mars, there is no backup, there is no neighboring town, there are no emergency services arriving within hours. A critical failure in any major system, life support, power, thermal regulation, becomes a countdown to death, measured in hours or days, with rescue missions requiring months or years to mount. Consider the launch windows. Earth and Mars align favorably for travel only once every 26 months. This is not a minor logistical inconvenience. It is a fundamental constraint that transforms every problem into a potential catastrophe. If a colonist develops appendicitis, they cannot be evacuated. If a critical component fails and no spare exists on Mars, the replacement cannot arrive for more than 2 years. If a solar storm damages electronics, there is no rapid resupply mission. The colonists must survive on what they have, with what they can repair, for 26 months until the next launch window opens. This is not exploration. This is imprisonment with extra steps. The technology gap between our current capabilities and what Mars colonization requires is vast and often deliberately obscured. We do not possess sustainable closed-loop life support systems. The ISS still requires regular resupply from Earth. We have never operated a nuclear reactor on another planet. We have never constructed habitats that can withstand years of thermal cycling, radiation exposure, and micrometeorite impacts without maintenance from Earth. We have never grown food in extraterrestrial soil at the scale needed to feed even a single person for a year. These are not minor technical hurdles. They are fundamental engineering challenges that will require decades of research, testing, and iteration. Yet corporate timelines and space agency roadmaps speak of Mars colonies within 10 or 15 years. This is not science. This is marketing. The gap between landing on Mars and surviving on Mars indefinitely is as vast as the gap between the Wright brothers' first flight and landing on the Moon. One is a spectacular achievement. The other requires the development of entirely new technologies, infrastructure, and industrial capacity. SpaceX promotional videos show gleaming domes and thriving settlements. NASA mission proposals outline ambitious schedules with crewed landings in the 2030s. But these presentations consistently gloss over the difference between visiting and staying, between planting a flag and building a civilization. Landing humans on Mars is achievable with existing technology, though extremely difficult and dangerous. Keeping them alive indefinitely is not. The life support systems alone require breakthroughs we have not yet achieved. The psychological protocols for isolation and confinement exceed anything we have tested. The medical capabilities needed to handle emergencies without evacuation options do not exist in portable form. This is not pessimism. This is honesty. When engineers are asked privately, away from cameras and press releases, they acknowledge these gaps. They speak of the decades of preparatory work needed, the testing that must occur on the Moon first, the advances in materials science, robotics, and biotechnology that must mature before Mars colonization becomes remotely feasible. The public timelines are aspirational at best, deliberately misleading at worst. They serve to maintain funding, generate excitement, and attract investors. They do not reflect engineering reality. Now consider the liability and political dimensions, questions that dreamers conveniently ignore. Who is responsible when colonists die? And they will die. Is it the private corporation that sent them? The government that licensed the mission? The colonists themselves who presumably signed waivers? What laws govern a settlement on Mars? Can a corporation own territory? Can it enforce rules? What happens when conflicts arise between colonists or between a colony and Earth authorities? History offers no precedent for private colonization of genuinely hostile environments, beyond the reach of timely intervention. When ships sank in the age of exploration, rescue might come from nearby vessels. When Antarctic bases face emergencies, evacuation is possible within days. Mars offers neither of these safety nets. The legal and ethical frameworks for who bears responsibility, who has authority, and who pays for disasters simply do not exist. And they will be extraordinarily difficult to establish given that Mars colonization serves no national interest, compelling enough to warrant the political capital needed to create international agreements. Who compensates families when accidents occur? What court has jurisdiction over crimes committed on another planet? If a colony fails and requires a multi-billion-dollar rescue mission, which government or corporation foots the bill? These are not abstract philosophical questions. They are practical barriers that will paralyze missions when lives hang in the balance. Corporations optimize for profit, not safety. Governments answer to taxpayers who will question why money is being spent on distant colonies when problems remain unsolved at home. The comparisons to historical human migrations reveal how fundamentally different Mars colonization is from anything humanity has attempted. When Europeans crossed to the Americas, they found breathable air, drinkable water, edible plants, and huntable animals. The environment was habitable. When humans settled the Pacific Islands, the Arctic, or the highest mountains, they adapted to challenging but survivable conditions using local resources. Mars offers none of this. Every breath requires technology. Every drop of water must be extracted or imported. Every calorie must be grown in artificial conditions or shipped across interplanetary space at enormous cost. Antarctica is often cited as a parallel. Humans live there year-round in scientific bases, but these bases are entirely dependent on regular resupply from the outside world. They are not self-sufficient, they are outposts, not colonies. And crucially, Antarctica can be evacuated within days if necessary. If every Antarctic base lost all outside support simultaneously, the inhabitants would die within months. This is not colonization. This is temporary occupation sustained by continuous support from a nearby resource-rich civilization. Mars colonization proposes to establish permanent self-sufficient settlements where none of the conditions for self-sufficiency exist. It is more analogous to attempting to colonize the open ocean floor or the upper atmosphere, environments where human survival requires constant technological intervention and where self-sufficiency is physically impossible given available resources. Yet even these comparisons fail because the ocean floor and upper atmosphere are at least accessible for emergency rescue. The economics and engineering do not merely present challenges, they present impossibilities, at least with current and foreseeable technology. The resources required exceed any plausible return. The engineering demands exceed our current capabilities by decades. The legal and political frameworks do not exist and will be extraordinarily difficult to create, and the timelines promoted by corporations and space agencies are aspirational fiction designed to generate enthusiasm, not realistic assessments of when sustainable colonization might actually occur. This is not to say humans will never set foot on Mars. We almost certainly will. Temporary visits, research outposts, even small bases sustained by constant resupply from Earth are achievable, though enormously expensive and dangerous. But colonization, the establishment of permanent self-sufficient human settlements, is not a matter of willpower or funding alone. It is a matter of physics, biology, and engineering reality. And those realities, indifferent to human ambition, remain unforgiving. In the vast silence of space, between Earth and Mars, between dream and reality, the numbers wait patiently. They do not argue, they do not compromise. They simply exist, immutable as the laws of thermodynamics, reminding us that the universe does not care about our desires. It operates according to principles that cannot be negotiated, cannot be inspired away, cannot be overcome by sheer determination alone. The economic and engineering reality of Mars is not a temporary obstacle to be overcome with better rockets or bolder plans. It is a fundamental barrier that separates what we can imagine from what we can achieve. And until we develop technology so advanced it resembles magic, until we find resources on Mars that justify trillion-dollar investments, until we solve problems we've not yet even fully articulated, Mars will remain what it has always been. Not humanity's future home, but a distant red light in the night sky, beautiful to contemplate, deadly to inhabit, and impossible to colonize in any meaningful sense of that word. The silence that follows these realizations is not comfortable. It is the silence of dreams deferred, of ambitions confronted by reality, of enthusiasm meeting the immovable wall of physical law. But it is also the silence of honesty, of clear-eyed assessment, of understanding that to truly reach for the stars we must first ground ourselves in truth. And the truth about Mars is this: we are not ready. We will not be ready for decades at minimum, and the financial and engineering costs may forever exceed any benefit that colonization could provide. In this silence, we are left not with despair, but with perspective. Mars remains an achievement worth pursuing scientifically. But colonization, the permanent settlement of humans beyond Earth, may require not just better technology, but entirely different destinations, or perhaps the recognition that Earth, for all its flaws and fragility, is the only home humanity will ever truly have. We've travelled far in this exploration, not across the vastness of space, but through the layered impossibilities that stand between humanity and the dream of Mars colonization. The radiation that would silently destroy our cells day by day, year by year. The atmosphere so thin it offers no protection, no breath, no shelter from the void. The gravity too weak to sustain our bodies, allowing our bones to hollow and our muscles to waste. The resources that exist only in theory, buried beneath frozen soil in quantities unknown. The psychological toll of isolation in a barren desert where every mistake could be fatal, and the economics that render the entire venture not just expensive, but perhaps permanently beyond our reach. These challenges do not exist in isolation. They compound, they multiply. Each problem makes the others worse. Radiation damage is harder to treat when medical supplies must travel millions of miles. Weak gravity accelerates bone loss, which makes radiation effects more severe. Psychological stress impairs decision-making, which increases the likelihood of catastrophic errors. Economic limitations restrict the technology needed to solve engineering problems. And so the cycle continues, each obstacle reinforcing the next, creating a web of impossibility so dense that no amount of optimism can untangle it. Yet this conclusion is not a rejection of Mars itself. The planet remains a worthy subject of study, a destination for robots and rovers, a laboratory for understanding planetary evolution and the history of water in our solar system. Scientific exploration of Mars is invaluable, but exploration is not colonization. Visiting is not living. Studying a place does not mean we must inhabit it. There is profound value in recognizing the difference between what we can learn from Mars and what we can realistically build there. Perhaps it is time to redirect our gaze, not away from the stars, but toward solutions that serve humanity's actual needs. Earth faces challenges of climate, resources, and sustainability that demand the same ingenuity we dream of applying to Mars. The technology required to terraform another planet could first be used to heal our own. Orbital habitats spinning to create artificial gravity could offer expansion without the tyranny of planetary wells. The Moon, just days away rather than months, presents opportunities for research and development without the crushing distance that makes Mars so unforgiving. And robotic exploration, advancing with each passing year, can venture where human flesh cannot, seeing what we cannot see, surviving what we cannot survive. So why does the Mars dream persist? Why do we cling to visions of red deserts transformed into green valleys, of domed cities and children born beneath alien skies? Perhaps it is human nature. We're a species defined by exploration, by the relentless push beyond the horizon. Perhaps it is escapism, the fantasy that we can leave our problems behind and start fresh somewhere untouched. Perhaps it is technological optimism, the belief that every problem has a solution if we simply try hard enough, dream big enough, invest long enough. These impulses are not wrong. They have driven humanity to remarkable achievements. But they must be tempered by reality, by honest assessment of what is possible and what is fantasy dressed in the language of engineering. There is a certain wisdom in accepting limits. Not every mountain must be climbed, not every ocean must be crossed, not every world must be colonized. Mars is a place of stark beauty, a monument to geological time, a reminder that planets can die and atmospheres can vanish. Perhaps it is meant to remain as it is, untouched, a destination for our cameras and curiosity, but not our cities. And perhaps that is enough. Perhaps that is even beautiful. The universe is vast. It contains wonders beyond imagination. Some we will visit, some we will study from afar, and some we will never reach. Mars may be one of those places where human presence is brief, scientific, and ultimately temporary. And in accepting that truth, we do not diminish ourselves. We simply acknowledge the reality of biology, physics, and the fragile nature of human life in the cosmic void. If you've made it this far through this exploration of Mars and its impossibilities, thank you. This journey has been long, detailed, and perhaps sobering. If you found value in this perspective, consider leaving a like to help others find this video. Comment below and let us know where in the world you're listening from, and whether you still believe Mars colonization is possible, or if this exploration has shifted your view. And if you're interested in more deep explorations of space, science, and the universe's mysteries, subscribe and join us as we continue to question, to wonder, and to seek understanding in the silence of the cosmos. The stars are waiting. But perhaps we're not meant to live among them all. Perhaps some are meant only to be admired from afar, beautiful, distant, and forever beyond our reach.